All right, students, thought I'd make a video so you can kind of go through and not only self-grade yourself, but also kind of get a correction for anything you feel you did wrong. And this will make me, work out the solution so that I can start grading. So I hope you did well here. Let's read these. The first one hopefully was straightforward to you. It has these 4 fixed charges, and it gives us the value and the little picture with the 4 of them. And then they are placed in the corner of a square, and they give us its length, okay? An electron is placed in the plane of the square at its center and released. And so right here is an unstable equilibrium. And so if you release it, it is not going to be able to stay right there. Technically, you might say, I could balance this pen on its nose and it would stay. But in reality, there's always going to be some imperfections, and it's going to go off in the direction of the instability here. And so in this case, gravity pulls it down, and in this case would shoot it up out of the plane and towards the camera here. Okay, and then it says, what is the speed of the electron when it is very, very, very far away here? And so hopefully this looks like a lot of the problems we did where we said things to this effect, where, we can get the change in kinetic energy because it's negative of the change in potential energy, and the change in potential energy is the charge that's moving. Let's call that the Q naught, that's the electron, times the change in the electric potential. And that's really then where this problem boils down to and is the hard part of our electronics problem. And so let's do the change in electric potential, because that would be then final minus initial. And so we learned here that the equation for the potential from a charge, a single charge, would be KQ over R. And in this case, then, so because of the symmetry, when this thing moves far away, it's going to be the same distance r from all 4 of them. So this will be the final potential. So I'll say final position. And then this would be the initial position. And in this case, we're saying this is really far away. And so as r final approaches infinity, this whole thing approaches 0. So the change in potential would be minus 4k, and this would be these q's, and r would be that initial distance away. And if this then is 1 millimeter, then this diagonal would be the square root of 2 times 1 millimeter, and then we'd have to cut that in half to say how far are we away, and it would be the same distance for each particle. So this would start us off by giving us a nice number to work with. So there's the 4. Coulomb's constant is 9 times 10 to the 9th. The charge of these negative ones is, where is it? Negative 2.52, and then pico is 10 to the minus 12. And then for the distance, let me just grab the calculator, square root of 2 times a millimeter, and then divide it by 2. And so this is a distance of 7.07 times 10 to the negative 4. Okay. Now the 2 negatives make a positive, so the change in potential is going to be positive. That's good. Electrons go towards positive potential. And then 5 times 9 times 10 to the 9th times 2.52 times 10 to the negative 12 divided by the last answer gives me about 128. 128, I'll call it 0.3 volts. And so there is the change in the potential. And like I said, that's the big piece, because then, coming back up to here, I could say, well, then if I take the opposite of the charge that's moving, that's the negative 1.602 times 10 to the minus 19 coulombs. and then times the change in the potential, which we just got 128.3 volts. That right there would be the energy. Notice it's positive, and then notice that a volt is a joule per coulomb, so we're going to get units of joules here. Then if we set that equal to 1/2 mv squared, and then we can solve for velocity. So let me take this voltage and then multiply it by 1.602 times 10 to the negative 19. So there's the energy. Let me bring the 2 to the other side. Let me also bring the mass of 9.11 times 10 to the negative 31. So there would be velocity squared. And so now if I take the square root, I'm at 6.72 times 10 to the 6 meters per second. All right. So conservation of energy, hopefully you saw that right away, straight out of chapter 25, working with potentials based upon charge. And so remember, we can get the change in potential either by adding up all the charges, which would be the most appropriate case here, or by integrating the electric field, but we'd have to integrate it, all the way from here out to infinity, all the way, and so that's probably not a good choice for this one, but in theory, should work. So again, hopefully that was straightforward. And likewise, hopefully at least 2A is straightforward. The hard stuff is when we get these continuous charges. So hopefully the first half is kind of a giveaway problem. But we have here a point charge. They give us its magnitude. Looks like there's a plus and a minus. We have a dipole. They are 2 centimeters apart. They're shown in the figure. What is the electric field, both the magnitude and the direction, at some point that is halfway between and 1 centimeter up? So somewhere right about here, we're trying to find the electric field. Now going back to my kind of burnt orange to represent the electric field from this one would be pointing away from the positive, and the electric field from the negative would be pointing towards it. And since these two fields would have the same magnitude because they have the same charge, they have the same angle, then the vertical components would cancel off. So hopefully kind of the first thing you do in here in step A is to say the electric field in the y direction is equal to 0. And then hopefully the second thing you do is to say that the total electric field is twice the electric field in the x direction from just one of them. Because again, in the x direction, you can kind of see the components add together if we kind of draw this one as what it's made out of. It's made out of a little bit to the right and a little bit up. Whereas this one down here is a little bit to the right and a little bit down. And so the up and downs cancel. That's why we made that statement. And they both have a right to them. And that's why we made this statement. Okay, so then it boils down to just a single calculation of getting the electric field from one of them, or at least getting the x component of one of them. And the electric field from a single charge looks like this. And if we want the x component, we got to have its angle. All right, and now we can put in our numbers. So here's the 2. Coulomb's constant is 9 times 10 to the 9th. The charges is the 2.54 times 10 to the minus 6 coulombs. That's this part here that says microcoulombs. Cosine of the angle is 45 degrees, because if I break this apart, this is 1 centimeter, and it goes up 1 centimeter. So we can see a quick 45 degrees, I hope. So there's the 45 degrees. And then the distance squared, well, again, we've got this 1 centimeter, so I'll put it like this. And then if we go along the diagonal of 45 degrees is root 2, and then we can square that. And now it's just a matter of punching in our numbers. So 2 times 9 times 10 to the 9th times 2.54 times 10 to the negative 6 times a cosine of 45. Maybe I'll separate these two. I'll divide the square root of 2 squared is 2, and then 0.01 squared, giving me a total of 1.62 times 10 to the 1, 2, 3, 4, 5, 6, 7, 8 newtons per coulomb. And that's the x component. And that actually would be enough. I suppose you could write it as a vector electric field to be I hat and 0 in the j hat. Now, the hard one finally here is figuring out when the charges are distributed here. And on this one, you can kind of see that it says each point, same amount of charge is now spread. So maybe if this was like kind of a blob of butter or cement, you take your cement trowel and you just now spread it out. And then the same thing here, spread it out. And so we've got this whole charge and kind of this darker gray here. And so that's all positive, that's all negative. Now, hopefully then, as we've done so many times in these problems, and this is, that hard part of that very first chapter, chapter 23, is we should look at, the symmetric twin is what I like to call it, because like we did up here in A, this little chunk of charge right there, if we call it like a dq and its symmetric twin dq, would make a field this way and a field that way, and same logic, this one would be right and up, this would be right and down, and the up and downs cancel off, and they would do that for every symmetric piece of charges we have. And so without doing much work, we will hopefully make this statement that the electric field in the y direction is equal to 0 based on that symmetry. And then also, kind of like we did in A, we could say that the electric field in the x direction total is going to be twice the electric field in the x direction we get from just, say, the positive charge. Okay? And so there's my electric field thinking. Okay? But this is going to take a little more thought. We can think of the electric field in the x direction as being made up of a summation of electric field in the x direction of each little chunk of charge. And so we've got to imagine chopping this thing into an infinite number of little pieces. And each one then is going to have some kind of, field pointing, and I'll just kind of measure that one. And so in this case, the x component is probably pretty small, although it's hard to predict whether the field here will be bigger or smaller than what we got up here, because in one sense, as I smear it out, the charges get closer, but in another sense, the angle changes. And I think the angle here is going to be more significant. So it wouldn't surprise me if we get a little smaller field, but it's kind of hard to really predict whether it'll be smaller or not. But I would then write it this way, that it would be the magnitude of the field from one of them and then cosine of that angle, where, this is that angle cosine. Again, like we were doing over here in part A. Okay. And then, of course, the summation for the electric field is really Coulomb's law again. It's Coulomb constant times a little bit of charge dq. R squared is the distance away. And then we have this cosine theta. And now we've just got to kind of work through and figure out how to do this integral. And maybe the first step, like we've done a lot, is to realize that if this is uniformly spread, then lambda, the charge density per length, is a small amount of charge over a small amount of length. And so that makes dq equal to lambda dx. And then r squared is this distance away. And so if we kind of pick some charge and call this distance over here x, where you might say x is going to start with 0, and then we're going to add up until we get to our 1 centimeter. And then this is our 1 centimeter. We would have this 0.01 squared plus an x squared using our Pythagorean's theorem. So that would be the that would be the r squared. And then cosine of it, we can look at this angle and say, well, that would be the x over the r, which, using that same notation here, that would be our r. So there's our cosine theta, x over r. And now we've switched everything into our x's. And so let's go ahead and pull out all this good stuff that is constants, and see that we have an x dx, and then we have a 0.01 squared plus x squared to the 3/2. Unfortunately, this is a pretty easy integral to do because it's a u sub, and you can just see the differential up here from the bottom one, so it's just screaming at you. U sub would work perfect on this. But I'll even say you can look it up in the Appendix B if you want. I got no problem with that. But I'll go ahead and do a u sub. So I'll say let u equaling 0.01 squared plus x squared, which then makes du equal to 2x dx. So this integral, this x dx right here, is 1/2 du. And then, of course, I picked this, so that this would be u to the 3/2 power. If I go ahead and bring it up to the numerator, it becomes a negative 3/2 power. And then that way, I've just got a power function to do. And in a power function, you add 1 to the exponent. So my negative 3/2 now become a negative 1/2. And then you also divide by that new exponent. So I guess the 1/2 would cancel, and I'll just bring the negative out over here. And so now I have u to the 1/2, and this will be okay. I'll go back and put my u as what it is equal to. And then with the 1/2, and technically it says negative 1/2, so I will bring it downstairs and then write it with a square root. And now I can then put the limits of my integration. And I probably should have put them here first, because this would be 0 to 0.01. And so 0 to 0.01. And so this becomes, let's see, negative 2 k lambda, and this would be then a 1 over, I guess it would be the square root of 0.01 squared plus 0.01 squared, and then minus 1 over 0.01. And I suppose then, maybe to save a little work on my calculator, I'll put the negative here and here. And now I can put in my numbers. So here's a 2. And then Coulomb's constant is 9 times 10 to the 9th. The charge density is that 2.54 times 10 to the minus 6 spread out over this length of 1 centimeter. And then I've got this 1 over 0.01 minus a 1 over, and if it'd be okay as long as I'm here, why don't I just factor out this 0.01, and then I will just have the square root of 2 left over. Is that right? Let's see, that'd be 2 of those. Yeah, square root of 2. And then actually, I guess I could factor out another 0.01, and then I just get 1 minus 1 over the square root of 2. So let me grab my calculator here and take this as a 1 minus 1 divided by the square root of 2. So that's that number. And then working backwards, maybe I will divide it by 0.01 squared, multiply it by 2.54 times 10 to the negative 6 times 9 times 10 to the 9th, and then times a 2. And I get 1.34 times 10 to the 1, 2, 3, 4, 5, 6, 7, 8. Yeah, and not a surprise, same order of magnitude, and slightly reduced, as I kind of predicted it would be, but very hard to tell it would be smaller, because like I said, as we spread it, these charges get closer, but we also change the angle. And we're so close, I think the angle dominates, and so I think, yeah, we should get smaller, and we did. So good. So 2B is a hard one. If you didn't get that one all the way right, don't beat yourself up with. That's pretty good. But hopefully you got the A. That was the intent anyways, to kind of set you up for the harder one, B, and also to give you a lot of points. And likewise for number 1, trying to get you hopefully started off on an easy one, straight off, and say, hey, just do conservation of energy. Although I suppose if you don't see the conservation of energy, it doesn't seem very easy to you. All right, let's try a capacitor one. This is our chapter 26. We got this circuit. This is the one that, at least for those of you who were in the live lecture, and I think we did a problem also on the video lecture this way. We had a long discussion on this. Ours looked a little different, but the idea is the same. And so we're going to study this figure, and so get an idea. And then first you close both switch number 1 and number 2, but 3 remains open. And so the key was to realize that when this switch remains open, no charges can go on here, and not even from this direction. This is, completely shut off, this branch, as we talked about, because, you might think, well, maybe this battery here is going to put a positive over here, or put the other way, it's going to suck a positive off. But it really can't, because as it tries to suck a negative off, it leaves a positive and it comes back. It only works when a negative goes on and the negative changes it off, so that the net charge is 0. Our electronics just shuts down if we start building up a positive charge. These forces are just so strong. And so given that this switch is open, nothing is going to happen here. Even though there's a direct connection here, and you might think at the potential, or potentially there's an option here, but there's really not. And so that was our discussion. And so you can just kind of ignore this at first and just say, okay, well, this is going to build up a charge. And so using the idea that a charge is equal to the capacitance times the voltage. And this is kind of our simple circuit, one battery. So this is going to build up until the voltage here gets the same as that, which is 50 volts. And so if we take the 8 microfarads and we multiply it by the 50 volts, we hopefully get 400 microcoulombs. And so that kind of tells us how much charge builds up on number 1 at the beginning here. Now, they don't ask for all that, so maybe I did too much math already, but it turns out I will need that. So I'll go ahead and just do the first kind of step. But see, then switch 1 is opened. And so again, here's the important part. When you open that switch, you cut off the ability of electrons to enter or exit this branch. And again, even though there's a connection here, and you might say, well, maybe an electron will move into here, or a second or a third electron. But see, the thing is, because another electron can't come off, that will not happen. Because once that first electron gets on there, it is just so powerful from stopping other ones to come in. And so whether we have capacitors or batteries, or in the next section, resistors, and the next section next unit, inductors, they never build up a net charge. And so that we got to have, when we talk about the charge on the capacitor or the charge in the battery, we have to remember we have an equal and opposite. There really is never a net charge. So that was the key to these switches. And so when switch 1 is then opened, we need to remember that none of these 400 are going to go back into this battery. They could shuffle over to here if they have a path, but at this point they don't have a path because switch number 3 isn't open until I read this sentence. Then switch number 3 is closed. So now they can start moving around. So now they can actually leave number 1 and go on to number 2. But again, they can't go back into the battery. And their wires don't go anywhere else. So the only option they have is to go on to here. And so what they're going to do is they are going to start to flood on here. And so this charge is going to go down. And so it's going to go down from 400. But this one now, the charge is going to go up. And if we call it Q1 and Q2, then what we know from conservation of charge is that it'll be 400. So yeah, they may shuffle around a little bit, but the total will still be 400. Now, how do they shuffle around? Do they split 50-50? And no, they don't. That was our discussion with capacitors. They would shuffle around until the push, so a bunch of negatives and positives on here, match the push here, negatives and positives. That means the voltage. The voltage is the push. And so it doesn't have to be the same amount of charge. It has to be the same voltage. So what we're saying here is voltage on number 1 and voltage on number 2 is equal. And using this idea of capacitors, the voltage on a capacitor is its charge over its capacitance. And so if I label this charge 1 and capacitance 1 and this charge 2 and this capacitance number 2, then they match up here. And in fact, now we can even put capacitor number 1 is 8 microfarads and capacitor number 2 is 4 microfarads, meaning that the charge on number 1 is going to be twice that of number 2. And so that's how they're going to redistribute in themselves. Or maybe put another way, because this one, number 1, has twice as much capacitance, one way of thinking about it is because the plate here is twice as big as the plate here. And so the electrons distribute themselves with an equal concentration. And as they distribute themselves with an equal concentration, because this plate is twice as big, they'll end up being twice as much charge on here. And so number 1 has twice as much charge. So again, that's why they separate themselves. They separate themselves based on a push, not the amount of charge. And so now the electrons are evenly distributed here and here, but not equal amount, because there's a bigger area. Okay, so now it's just a matter of finishing the calculations here, because we have 2 equations and 2 unknowns. And so if I put Q1 up to here, I get 2Q2 plus Q2 equals my 400 microcoulombs. That, of course, adds up to a 3. Bring that 3 over to there, and that's about 133 microcoulombs. And so if we double that, we're at 266, and if it's actually, I guess, 66.6, I'll round it up to 67. And so there would be the 2 charges. Nice. And in fact, the ratio of these capacitors is the same ratio that we saw in the example problem. So that hopefully went well for you. But again, you got to think about the physics of the switches there. So that can be a little bit of a challenge. All right, well, let's try here number 4. Number 4 is kind of the classic problem, and you saw it on the practice exam, that, some kind of circuit and find the charges on each. And on this one, it looks kind of hard because it's got 5, but it actually comes out to be even simpler than the ones that was on the practice exam. In fact, I think most of these problems are simpler than the ones on the practice exam here. So I would do this. I would draw an equivalent circuit right away, and notice that 1 and 2 are in series. And so that's, kind of the skill you're developing. That, okay, how do I know something in series? And if you just draw a line, that means the electrons from number 1 can only go to number 2. It's a single path there. And that means they're in series. And so I could get the equivalent capacitance of number 1 and number 2. And then by that same logic, I have the equivalent capacitance of 3, 4, and 5. See, whatever comes from 3 has to go into 4, and from 4 into 5. And so these are in series. And if you remember, when we do a series, we do that reciprocal sum. And so the equivalent capacitance is the reciprocal of the first one plus the reciprocal of the second one, and then the third one, and fourth or fifth if we have it. It's like we're going to have a 3 for one of them and 2 for the other. Then once you get that total, you take the reciprocal of that. So using my calculator here, I'll go 10 and take the reciprocal, and add 20 and take its reciprocal, hit enter, reciprocal of that. Gives me about a 6.67 microfarad for the equivalent of 1 and 2. And for 3, 4, and 5, it would be 30 reciprocal plus 40 reciprocal plus 50 reciprocal, hit enter, and take the reciprocal of that. And it looks like we are at about a 12.77 microfarads. Now we could even notice that these two are in parallel and we can add them, but that's not necessary because ultimately the goal is to find out what the charges are on each of them individually. And so the more I condense this together to the equivalent circuit, the more I get away from the real circuit here. Because when they're in parallel like that, we know they have the same voltage. And so I'm going to use that to say, okay, let's find the charge on the 1, 2 equivalent. In other words, let's find how much charge comes out of the battery and goes down this path. Because that would then be the equivalent 1, 2 and its voltage. So the equivalent is the 20.67 and the voltage is the 20 volts. And so taking the 6.67 here and multiplying it by 20, and we're looking at 133.3 coulombs. And if we then take that thought process saying this is how much, 133.3 microcoulombs comes out of the battery and flows down here, or if you want to think about it in terms of electrons, go this way and pile up negative and chase off equal amount here, then we can then bring this back up to here and say, well, then that's the number of electrons that come on to number 2. And so this is actually telling me that the charge on number 2 is 133.3 microcoulombs. But as we said earlier, that would have to flow and go from number 2 on to number 1. And so as these electrons pile up on number 2 and chase off electrons, they go on to number 1, and it's the same amount. So we were saying that in series, they would have the same charges. Good. See, and I can also apply that same logic here to this equivalent capacitance 3, 4. So the charge on 3, 4, 5 would be the capacitance 3, 4, 5 times its voltage. And so that's this 12.77 and then times the 20. And so this would be 255.3. And again, the logic being that's how many electrons would come out and go down this path. And if when I go back to the real circuit, that's how much would come out and go onto that path. So that's capacitor number 5. So 255.3 microcoulombs. And then again, by that same logic, that's how much then would come off So I'll put a bunch of electrons coming on number 5, chasing off the same amount. Then they go on to number 4. And so number 4 has that same charge, 255.3. And then it changes off the same amounts that it puts on. Remember, you have to keep it neutral. Otherwise, things will just shut down. The forces will be too great to stop any more from coming on or going off. But then it goes on to number 3. And so number 3 builds up a negative charge. And again, it must be that 255.3. Now, by the way, if you had put these two together in one giant equivalent one, then you would have solved for the total charge coming out of the battery, which I guess would have been these two added together here. And nothing's wrong with that. You just would work backwards to this step and then from this step back onto here. And so I didn't need to really go to that step. And that might be the key to this problem right now, because once we have any two of these, we can find the third and then also the fourth. So we only need 2 in a row to find the other 2. And sure enough, we have them using, this relationship that the voltage is the charge divided by the capacitance. So in this case, I would take this charge and divide it by a capacitance, and dividing by 10, I won't need my calculator for that. And so that's 13.3, and I guess I'll do 3.3 if you want. And then the 133.3 divided by the 20 for the second capacitor would be the 6.67. Now, maybe this is worth pausing and kind of checking. No, let's keep going. We'll do a check in a moment. But these are the ones that I said that you can check these real easy, and then you'll know if you did them right or if you did them wrong. If you learn you did it wrong, that doesn't necessarily mean you'll find the right path, but at least you know about it. But let's just do the other ones. This is 255.3, so if I divide it by 30, I get 8.51. If I do the same mathematics but divide by 40, I will get 6.38. And then same mathematics, this time divide by 50. I will get 5.11. Yay! All right. And now I can do the energy. But before I do that, why don't I just check if things seem to make sense here? Because we can look at things that, series and parallel. And really, we just have those two in series. Do they have the same charge? Yes. Those three? Yes. In fact, that's how we derive them. So those check out really well. The other one is the discussion of maybe, you reminded me of, my analogy of gravitational potential energy where, somebody parks a car here and one person goes for a little hike to the summit and the other person takes another path to the summit. You should go up the same amount. So from here to the summit is through the battery. That's up an increase of potential of 20. And so that means from here and then here again, that the two ups, and you can see from negative to positive is an increase in potential, and then negative to positive is another increase in potential. And so these two increases should add up to 20. And so do these add up to 20? And yes, they do. So that makes me feel good about those. And then likewise, if we had a third person in our hiking group, that third person can go off this way, and they'd go up and then up and then up and get to the summit. So the 3 of these should add up to 20. Notice, by the way, I never said that all 5 of them should add up to 20. But these should, and I think they do. That's a 10, carry a 1, 8, 9, 10, carry a 1. So that's 0, 0. And then 11, 19, and the 1 is a 20. Yay! Okay, so those 3 add up to a 20. So I'm pretty sure I did this correctly. I suppose another quick check here, not needed, but if I had done the equivalence of these two, I would just add them together. So 12.77 and 6.67 give me a 19.8 0.44. And so if I was looking for the total charge coming out of the battery, I'd take that capacitance, multiply by 20. And so we're looking about 388.8 that comes out. And then that's what these two should add up to be. Let's see, a 3, an 8, an 8, and an 8. Perfect. And so those two add up. So there's another reason I would be happy with that. And in fact, just getting ready to kind of double check things, I guess I could say then the total energy here would be 1/2 CV squared. And so 1/2 times my C times my V squared should come out to be about 3,888 microjoules of energy. And that's what comes out of this battery. So all of these energies, and notice all of them have to add up to that. That's conservation of energy. Notice the voltage doesn't. Those are your pushes, but your energy does. But let's just kind of get the energy of each individual one. It's 1/2 times C times V squared. And so this is about 888.4. 1/2 times C times V squared would be 444.9. 1/2 C V squared would be 1,086.3. 1/2 times C times V squared here would be 814.1 microcoulombs. And then finally, 1/2 times C times 5.11 squared should be 652.8. And that, I guess, would finish the problem. I suppose I could double check here. Let me get this energy. Add it to that energy. Add it to that energy. Add it to that energy. Finally, the last one's way up here somewhere. What was it? 800. There we go. Add it to that one. And I get 3,886, which, other than some rounding, I think it matches there, at least to 3 significant figures. So, feel really good about that one. Yay! So, I can move on to the other problems that are giving me stress on the test. Okay. And now off to the last one. And this last one, number 5, is a little bit like number 2, where hopefully the A is straightforward. We did a lot of this, and so it's kind of just a plug and chug. But then it gets real hard when we spread out the charge, and so 5A to 5B. And B is going to be a little harder. That's why, at least for you guys in class, I gave an extra sheet of paper here. I said, oh, this is going to take a little bit of space, if you will. But for A, we just have a uniform charge density. It's real long. We're a certain distance away. We derive this equation twice, and you can just start right by looking it up. Now, if you want to do Gauss's law and do a Gaussian surface, you could say the integral of E dot dA around a closed surface And do something like this. You can say the electric field with the correct Gaussian surface is a constant, if you remember doing those. And then the area, when you wrap around a little, Gaussian surface around it, the area of this one would be like unfolding it, and so it would be its length, which is 2 pi r, and then if we draw it a length of L, that would be then cosine of 0 degrees, because the other pieces have 90 degrees. That is a closed surface. If you did your Gaussian, you got this top and this bottom. So without trying to take too much time to rederive this, that's how you do Gauss's law. Oh, and then I guess I should do the other side. Lambda times its length, epsilon naught. That's 0. That's 1. L's cancel off. And then you get E equals 1 over 2 pi epsilon naught, lambda over R. And then if you multiply top and bottom by 2, this 4 pi epsilon naught is Coulomb's constant. So you get 2 times Coulomb's constant times lambda over R. Now, it's harder to do it by Gauss's law. We had to integrate a bunch of points. We had a dq, and another dq, and another dq, and another dq, and another dq, and another. In fact, it looks very much identical to, well, not identical, but very much like number 2, where we had up this line of charge. The difference is we would go infinite, and also the difference is we wouldn't have a plus and a minus. We'd have a plus the whole way, and so what ends up happening is the x cancels off and the y doesn't. But like I said, I think most of you, when I get to grading it, are going to just put that down and just say, hey, well, we know that one, and you're right. And so go for it. That's not the hard part of this problem. That's why I put the B to kind of test you on your thinking, whereas A is just test you on your reading and your just, did you do the homework and understand the homework here. So feel free to start right there and just plug in your numbers. So this would be a 2. This would be 9 times 10 to the 9th. This would be your lambda, and then the charge per unit length is directly given, 3.25 times 10 to the minus 9 for the nanocoulombs. And then the distance away is 0.0022 meters. And so, like I said, hopefully this one went quick and easy, because as a couple of you said to me at the end of the test, goes, yeah, I plowed through this without much worry, and then I got to this one, and I spent the rest of the time on this one. And I get it. I get it B. But anyways, let me get an answer here for A. And so 2 times 9 times 10 to the 9th times 3.25 times 10 to the minus 9 divided by 0.0022. Let me just check that. Is that what I said? Millimeters? Yeah. And hit enter. All right, so it looks like we're about 26,600-ish. So I'll just put 26,600 newtons per coulomb for the magnitude of the electric field for part A. Now, part B is kind of that smearing effect again. So if you can kind of, imagine this time, I guess, would be a kind of a strip of butter or a strip of cement or stucco. And so you put it on, and then you take the trawl, and you're going to kind of spread it out evenly. And you're going to get then a strip. And so it kind of helps to picture that. In fact, you've heard me say that many times, that really physics is about knowing how to apply a few but powerful fundamental concepts to explain a universe of phenomenon. And so here we have something that I don't think we ever saw. I don't think there's an example like this in the book, and yet you can do it. Because you're going to apply this just adding up the fields. Now I'm going to help you out here. It says if the rod is now stretched in the negative x direction to a width of, so let me just call this W for width, but it's 1.5 centimeters. The charge per unit length in the y direction remains the same. So in other words, as we spread it towards the negative direction here, that charge that, was, say, right here, right here, now just gets elongated. Now, the reason that's helpful here, it says, let's see, to a width of the charge to form a strip. What is the magnitude of the electric field at this same place? So we're still looking at a distance of 2.2 millimeters out. And I suppose the scaling doesn't match here, but I think you get the idea. We're actually kind of close compared to the width. So this was quite a bit of spreading. And I give you a hint, two really. The sum of an infinite number of thin rods makes a strip. So A, again, is setting you up for B. I hope that did anyways. That's kind of the idea, kind of like in number 2. If you think about a point, these are the kind of point fields that you learn kind of in, your first physics class. And then your second physics class, we do a little bit more. We have calculus now. We kind of spread it out. So maybe this is a high school problem, and then a college problem. And then, of course, you'll have your upper division problems, which will be even more advanced, depending on what your major takes you. Okay, but there's the idea. Kind of spread this. And so I'm going to think of this, as the hint says, as made up of a rod and another rod and another rod and another rod and another rod. And so I guess I would write it mathematically like this. I would say, okay, the electric field from a strip is the sum of the fields from a rod. And now I can go back to this equation for a rod, which is 2k lambda over r. But let me be careful with this, and then here's a second hint. The lambda of these infinite rods has now been diluted. You see, you can kind of see it in this picture that if I took this charge and I kind of swiped it, now this charge per unit length right there is much less because it has, been distributed out. So maybe just for discussion, let me give it a different symbol. How about like a lambda prime? I hope you won't think of that as a derivative. But it's diluted, it's thinned out, it's reduced. Now, it's been spread out kind of uniformly here, so it's going to be the same for every rod, so I'll keep that in mind. The other thing I'll keep in mind is this R value is the distance from the rod, and so as I add them up, there's going to have different distances from the rod. If we kind of add them from the right to the left, the first one would be a distance of our 2.2 millimeters. But then I'd add up the next rod and 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 the next rod. And eventually I'll get to this last rod, which would be the 2.2 millimeters plus the 1.5 centimeters. Okay. So that's going to be a variable. And then, of course, to make it continuous, I really want to change this into an integration. I really want to kind of smooth this together. And that's where this lambda prime can kind of come into place. Because this is, a density. And we've done this quite a few times, and it's maybe worth seeing one more time, because it certainly won't be the last time this semester. We'll keep doing this over and over again. But I really think that's why these first couple of chapters are kind of the hardest ones of the the whole sequence of physics 121, 122, and 123. Because this is the first time we're doing it, and it won't be the last. We're going to do this all the way through, and we're going to get into magnetism real soon here. And we're going to keep doing this. And then we're going to get into electromagnetism. We're going to keep doing it. And so what I like to say is kind of like finding the mass density of a chocolate bar. You can take the whole chocolate bar and divide by the whole, take the whole mass of the chocolate bar and divide by the whole volume of the chocolate bar. Or you can break off a little chocolate square, and so you have a little bit of chocolate. So you take a little bit, that little mass, and divide it by its little volume. But the ratio is the same. And kind of what I'm saying here is, if you think about this, little piece here that has now been spread out, we've got the lambda here that has now been spread out over a whole width. And so you might call this the whole charge over the whole width. That must be the same as one of the pieces. So let me grab this rod right there and color it in. Okay. So that little rod would have a small amount of charge, and I guess I would spread it out over some small distance. Let me just call it delta x. And this helps me because I can now get the important piece here, that this lambda prime would be lambda divided by w times however thick you make it. In fact, if it helps, you probably could have guessed this. You probably could have written it as the amount of charge density on a little piece would be what you started with times some kind of fraction, some kind of ratio. And it would be the part over the whole. And so the part being, how much of a width of this little rod do we take, delta x, divided by its whole width. So that's a fraction of all the charge multiplied by all the charge gives you the charge on just one little piece. Well, let me use this or this, whichever one you like, but I'll take this one and put it up to here. So this becomes a summation. And so this will be 2 times Coulomb's constant. And now I can write this as a lambda over a w times a delta x. And as long as I'm mentioning x's, why don't I then just call this r the x, right? Because the r is how far is it along the x-axis away. So x. And as we said earlier, our first value of x will be 2.2 millimeters, and then we'll keep adding our rods until we get to this r plus this w. And so that's, the tough stuff. That's what we saw in chapter 23 is, how do we do things like this? How do we change an algebra problem into a calculus problem? Because the next step here would be take the limit as delta x goes to 0. Imagine cutting these rods thinner and thinner and thinner and thinner and thinner and thinner and thinner. Because when you take that limit, the delta x going to 0 then becomes the dx. And the summation becomes the integral. And so then we've got the 2 times Coulomb's constant times lambda. And if it'll be okay with you, I just wrote the lambda over w with the w down here, so I have a wx. And then setting up my limit, I guess I'd go from r to r plus w. So I can pull out the 2, the Coulomb's constant, the lambda, and the w. And then I have an integral of dx over x. So that's ln of x, evaluated from r to r plus w. And maybe before I put in my numbers and finish it up, I'll just take those and put in the limits and take care of the property of logarithms. When I have the log of something minus the log of something, I can write it as a quotient. All right, so now I'll put my numbers in. So this is a 2. This is 9 times 10 to the 9th. The original charge density was the 3.25. 3.25 times 10 to the minus 9. The W is that width. I think that we said 1.5 centimeters, right? Yeah. So let me write that as 0.015 centimeters. And then I will have the natural log, 0.0022, because it was 2.2 millimeters. It's got to make sure I get these the same units. In fact, it's a ratio, so I don't even have to change it to meters, as long as they're all centimeters or all millimeters or all meters. But just to avoid confusion, I'm going to change them all to meters. Because 1 and then the 5 make a 7.2 there. And so there's my adding them. And so let me grab the calculator now. And maybe I'll do this one first. Natural log 0.0172 divided by 0.0022, enter. So there's the natural log. And then maybe working backwards again, I'll divide by 0.015, multiply by 3.25. In fact, I'll just save myself a little bit of calculator work and cancel those, won't even mess with them, times a 9 and times a 2. And by the way, I didn't make a prediction, probably should have, but I'm thinking that this should be a lot less than what I got in part A, because in part A I had the same amount of charge, but then I kind of smoothed it out, and so as I was smoothing it out, I was moving all those charges further away. And so the strip that remains close has very little charge, and all the other ones certainly add up to that charge before, but they're each further away. So I would expect a significantly lower electric field in B than what I got in A, and maybe a little more than 3 times lower, sure enough. All right, that's it. Hope you did well. Take care.